Okay, video is rolling. All right, so we're going to buy chicken that costs $3 a pound. Here I was to find some variables. How did I do? X equals the total weight of chicken to be purchased in pounds. Y is the cost of the chicken in dollars. How did I do defining those variables? First criteria. Is it a quantity? Second criteria. Do you know exactly what quantity I'm talking about? Yes. And do I have units? We're good, okay? So I got two good variables to find here. And I'm going to start, and what? Variables vary, right? Variables vary. X can take on any weight of chicken that we could choose to buy. So I'm going to choose to buy 1 pound. Okay? The current value of X is 1, but it can change. It can change, and it's going to change, okay? What is my current cost? $2. Too easy. Okay? Now the value of X is 3. It means there's 3 pounds of chicken on the scale. Variables vary. Variables they stand for every value of the quantity that it could take on. Okay? Current value of Y. Okay? And what's happening? As I'm doing this, I'm getting points. This point right here, what does it mean? What's the meaning of that point on this graph? This one lower left here. When you have 1 pound of chicken on the scale, you're going to pay $3 for it. It's the corresponding values of 2 quantities taken together. That's what a point gives. A point is showing the corresponding values of 2 quantities taken together. Okay? 7 pounds. How much? 21. 12 pounds. Okay, and so every time I have a value of X and the corresponding value of Y, I can show that as a point on the graph. I can show that as a point on the graph. And then, of course, there's more choices I can make. Here's a bunch more. Is this all the possibilities? No. I could do even more. And as I plot more and more and more of the possibilities, wow, why? Oh, I didn't copy that. There we go. As I plot more and more possibilities, something emerges on our plane. What emerges on our plane as I continue to include more and more points for more possibilities? A line, a graph, okay? A graph. And so this graph represents all possibilities of an amount of chicken, a weight of chicken in pounds, and the corresponding cost. Each one of those is displayed as a point. Okay? So I can go back to this. And so you're used to seeing lines that look like that. And when you look at that line, it's like someone took a ruler and a pencil and went, what are you looking at when you look at that line? Did you learn something in the last 30 seconds? What are you looking at when you look at that line? What is it? He wants all the possible points. Okay? So, you see this. Oh, no. Wrong way. You see this. And you think that, or sorry, that's not what I meant to say. So you see the line, you see the straight line, and you think points. Okay, you think points because that's what that line represents. It's not a stick or a wire that you can move and bend and move around. It represents points, and each point is the pair of two quantities taken together. Let's go back and add our line back on there. Okay. All right, so now we want to look at, so we've got this line, and we know when we're looking at that black line, we're looking at all these different points, these possibilities of an amount of chicken in pounds and the total cost in dollars. So what I want to do is, I want to start a new table here, and I want to look at some changes here. So if x changes from 1 to 3, we want to finish the line in this table here. And you're going to use, to do that, use this table over here. Okay, so to finish the line in the table, we're going to use our original table of corresponding values of x and y. So as x changes from 1 to 3, what does y change from? From what to what?
3 to 9.
It changes from 3 to 9. When x is 1, y is 3. And then when x is 3, y is 9. So y is going to change from 3 to 9. So what scenario in the grocery store does this represent? What scenario in the grocery store? This very simple and obvious. Okay, so here in the grocery store, and what just happened? Where were we, and what happened, and where are we now? Okay, but give me all the details. All the details. Yeah.
We had 1 pound of chicken, and then we picked up 2 more pounds of chicken.
So now,
We have 3 pounds of chicken.
that's it. We were at the scale, and there was 1 pound of chicken on the scale, and then we said, butcher, give me 2 more pounds. And they took 2 more pounds and put it on the scale. And then as that happened, our cost did what? It increased from 3 to 9. So what was the delta? So you guys are experts at delta x now from your web work, right? You're experts. What is delta x in this scenario? Right. And what then is the corresponding delta y? So let's show that on the graph. We want to represent that first line in the table on the graph. So where did I start? I started at 1 pound of chicken costing me $3. And which point is that? A, B, C, or D? Which point, A, B, C, or D, is 1 pound of chicken costing me $3? A. And so from A, I want to show a change in the amount of chicken from 1 to 3 pounds. I'm just showing the change in the amount of chicken, or the change in x, from 1 to 3. How do I show that? Okay, right, horizontal. So from there, horizontal. Horizontal is my x coordinate, and vertical is my y. So I'm going to draw a horizontal line. Best horizontal line I've drawn all day. Okay, from 1 to 3, and that's my delta x of 2. So that horizontal line is showing that I started with 1 pound of chicken and I just changed my pounds of chicken by 2, or I increased the amount of chicken by 2. But then as that happened, what did we say? Y changed by from 3 to 9. So how can I show that? Yeah, so at the same time that happened, we also had an increase in y. Delta y equals 6. Okay, calculus is the math of change. Okay, and so we need to represent change visually. So this is how we can show change visually. We show that x increased by 2 and y simultaneously increased by 6, and we can show that with a horizontal line for the change in x and a vertical line for the change in y. Okay, so now I want you to, I'm going to give you these changes in x. And you're going to do these 3 lines in the table, and then also update the graph for those 3. No, just two, sorry. Let's just do 2 lines. So those 2 lines in the table, and then the corresponding way that you would update the graph, that you would represent those 2 lines on the table on the graph, okay? And I always encourage you, when I put you to work in class, unless I say otherwise, you should work with those around you. So definitely share what you're doing, check your work, ask questions, and then also LP can walk around and see if you have questions also. Place. So, changing from 1 to 7, do I start at point A, B, C, or D? Or sorry, from 1 to 7 means Y changes from? You just read the table. 3 to 21. And from 1 to 7, if X changes from 1 to 7, the change in X is? Final minus initial, right? Final minus initial. And then the change in Y is? 18. Piece of cake. Let's draw it. I'll do it in red. I'm going to start at point A, B, C, or D. I'm going to start at A again, and I'm going to go which way and how far? I'm going to go horizontally to the right 6 units until I reach X equals 7. And that's my delta X of 6. And then from there, I have the corresponding change in Y of, which I show going up. Delta Y equals 18. That's line 2 in the table. A change of X of 6 means a change in cost of $18. And then finally, from 7 to 12, what point am I going to start at? A, B, C, or D? Well, let's do the tail first. So when we change from 7 to 21, the cost changes from 21.36. It's right there in the table, right? You just look at the table. The change in pounds, if we go from 7 to 12, 5. Corresponding change in cost from 21 to 36, 15. And you told me I'm going to start at point A, or sorry, point C, and I'm going to go which direction, how far? Right, 5. Delta Y equals, delta X equals 5, corresponding delta Y, 15. Okay, so hopefully that's pretty straightforward, that's pretty easy, but I would guess that many of you have never done anything like this before. It was just Y equals MX plus B, and that was it. So, but understanding what's going on here is about analyzing changes, analyzing a change in this case, the change in the pounds of chicken and the corresponding change in the dollars. And we want to represent that visually. We want to represent those changes visually. And that's what we can do. Okay, so now I got a new one. X changes from 12 to 3. X changes from 12 to 3. Is it realistic? Is it feasible in the real world?
Yeah.
Okay, so someone describe to me what exactly, specifically, what that would be in this scenario. X changes from 12 to 3. What would that mean?
You'd be going from buying 12 pounds chicken to 3 pounds chicken, so instead of increasing the mounted cost, you'd be decreasing, so it'd be a negative number.
Okay, what was it? What's it?
The cost.
cost would be a negative number.
Or the change.
Change, right? So she said you'd be going from 12 pounds. So 12 pounds are sitting on the scale, and we say, butcher. What do we tell the butcher? Take off how many pounds? 9. We're going to take off 9, and mathematically, that is the value delta x of negative 9. It still follows final minus initial. 3 minus 12 is negative 9, and that negative signifies a decrease. You can't have negative 9 pounds of chicken, but you can have negative 9 in terms of a change in the pounds of chicken, which means a decrease. All right, and what happens to our cost when pounds goes from 12 to 3? 36 to 9, which is a change in y of 27. Is that right? Negative. So when the pounds goes down, our cost goes down, right? If we buy less, we're going to pay less. And so that's the changes, negative 27. So we're going to draw then the graph. Am I going to start at point A, B, C, or D? A, B, C, or D? D. And where am I going to go first? Left first. So lots of times students want to go up and down first. What happens? The first thing that happens, or what we initiate here, is changing the number of pounds, which is a horizontal change. So we're going to start here, and we're going to go left to how far? I went too far. There? And that's my delta x of negative 9. If you want, you can even put a little arrow there, showing that we started here at the right and we moved left. And so we decreased x. We decreased x by 9. And when that happened, as that happened, what happened? We decreased y by, so delta y is negative 27. Okay, so being able to show changes with these quote unquote triangles, two sides of these triangles, is important. You have to be able to show changes, okay, and know what it represents in the situation. Okay, any questions on that? All right, so looking at these pairs of changes, so we've got 2 and 6, 6 and 18, 5 and 15, negative 9 and negative 27. So looking at those pairs of values, we have something that you studied back in middle school or junior high. What principle do we have going on there, looking at those numbers in pairs, 2, 6, 6, 18, 5, 15, negative 9, negative 27? Okay, what about the ratio? So she said ratio. Okay, that's a good start. And what about those ratios? Yeah, so do you see what happened? What is true about this ratio for all those? My question, what's true about this ratio? Delta y divided by delta x, the change in y divided by the change in x. It's 3. It's 3, always. This is the idea of proportionality. Okay, we have what do we have here? We have proportionality in the changes of two quantities. We have proportionality of the changes in two quantities, and that's what we need to have in order to have what's called, more room here. Okay. There we go. Okay, so when changes in y are proportional to changes in x, what do we have? We have what's called constant rate of change of y and x. Okay, so when changes in y are proportional to changes in x, that's what we have. We have constant rate of change of y and x. So lots of students get confused because we're talking about the changes. They think we have constant rate of change of the change in y and the change in x. No. So what we're looking at constant rate of change of these quantities, x and y. We're looking at these quantities, and in order for x and y to be in a constant rate of change relationship, it's about the changes in those quantities that tells us whether or not you have constant rate of change or not. Okay? So there are 3 mathematical results of this. Here's the first, and this is the one we just talked about. That the change in y over the change in x is constant. All right, that's kind of how we started. We said the changes are proportional, right? The changes in x and y are proportional. Okay, so when we say constant rate of change, there's kind of 2 different ways that we mean. So we mean it as a principle. So in this example, we have the principle of constant rate of change at work. But then you can also say constant rate of change is a particular value. So in this case, that ratio is the value of the constant rate of change. Okay? So we use that phrase constant rate of change in 2 ways to mean just an important overarching principle that in some situations we display that, we have that. But we also use that phrase to mean a value in that situation. And so what is the value of the constant rate of change in our chicken example? 3, okay? 3. That the change in cost per change in number of pounds will always be 3. And that constant value is the constant rate of change. Okay, our second mathematical result is that the change in y is a constant multiple of the change in x. In other words, delta y equals k delta x. Okay, so what do we mean by this? What we mean is if you're given a change in x, in this case a change in weight, you can always get the change in cost by doing what? Multiplying by 3. So if your change in weight is 5, you multiply 3 by 3, it gives you the change in cost 15. If your change in weight is 6, multiply by 3, it gives you the change in cost 18. If your change in weight is -9, you multiply by the constant rate, you get a change in cost of -27. Okay? And then the third mathematical result of constant rate of change is that if you apply equal changes in x, so if I add 7 pounds to the scale, no matter how I do that, so if there was 1 pound on the scale and I added 7, or if there was 10 pounds on the scale and I added 7, or if there was 15 pounds on the scale and I added 7, the same change in x will always result in a consistent change in y. So for instance, no matter for what situation I put 7 more pounds of chicken on the scale, what is my delta y going to be? My cost is going to go up 21, no matter what. No matter how much chicken was on before. Okay, so memorize it. So students who understand constant rate of change have these principles on the tips of their fingers when they're doing problems. So you're working through a situation, and they're not focused on getting the next answer. They're focusing on looking at the situation and seeing how these things apply. You have to take initiative on your own to make up little questions for yourself and make up little scenarios within a given context and prove to yourself that all these things are true. Okay? But in order to do that, you first have to know it. So as knowledge, first you have to memorize it. Okay? But then the key thing is then apply the principles. Not only to solve problems, but then just to analyze situations, like we just did. So then apply to solve problems and analyze situations. So don't just say, oh, I'll just fall back on my understanding of lines, what I've learned about lines before, linear relationships and constant rate of change, because we're going to ask you questions that see if you understand this. So you have to learn. So I'm trying to learn something new, right? Learn something new, and then you're going to be assessed on your knowledge of this and your ability to use it and apply it and reason with it. So this is a way of reasoning about linear relationships, not just solve certain types of problems and get answers. Okay. All right. So let's put you to work on a new example. Any questions on this? So again, constant rate of change means, in essence, it means proportionality of the changes of changes of two quantities. And here we have three mathematical results: that the ratio of changes remains constant, that the change in y is a constant multiple of the change in x, and that whenever you apply the same change in x, you're going to get a consistent change in y. Okay, new scenario. So here you got a soldier lowering American flag, top of a flagpole that's 14.5 meters tall. All right, so my number one, so the blue, all the blue text is what your tasks were, and so number one is done for you. But I don't want to de-emphasize the importance of you being able to write well-defined variables. That was supposed to be task number one, but for time's sake, we want to make sure we get to the new stuff. So make sure you can define variables well. You know all the criteria. So t is the time elapsed in seconds since the flag began to be lowered. That's a changing time quantity. And then h then is the height of the flag above the ground in meters. And so then delta t as a variable is the change in time elapsed since starting to lower the flag. And delta h is the change in the height of the flag above the ground in meters. So that's number one, is done for you. Here's number two. Number two is using these values here. So we're not assuming constant rate of change. Okay, we're not assuming that. All we have is these data values for a time and a given height, and another time and a given height, and another time and a given height. So we're not assuming constant rate of change, so we're going to just purely use this data. And I've written out several delta t's here. And so you're going to find starting and ending values of t that have that delta t. Does it make sense? So for instance, this first one, 1.5. Where do you see in the table a starting and ending value of t such that delta t is 1.5? Yeah, right there, that right there, 2. So we can all do that one first. 2 to 3.5. That makes a delta t of 1.5. And then based on the t's that you pick, then you're going to go back to the table and look at the h's, and you're going to calculate the change in h according to the data. And then you're going to go back to the table and look for another change in t of 1.5. Go to the table, find the corresponding change in h. This is number 3 now. And you're going to do that for all of these changes in t. Calculate changes in h. Okay? And then when you're done with that, then we're going to analyze. We've got all these changes. We're going to analyze the situation based on our 3 mathematical criteria of constant rate of change, which we just said, and we just laid them out. Okay, so you've got some work to do here. I'm going to keep taking attendance. LP can walk around and help you. You can work with each other. I encourage that. Okay, but this is the kind of analysis that you want to take the initiative to do on your own when you're given problems. Not just, how do I get this answer and how do I get this answer? You have to be able to unfold a situation and analyze it in the lens of constant rate of change. Okay? Go. Okay, let's spin the wheel. Where's Bryce? Bryce Coffee. All right. Tell me another change of 1.5 that you did. 3.5 to 5? And then what did you calculate the change in H for that? What did you get for that corresponding change in H? Or what would you do? What would you do? What minus what? So T is changing from 3.5 to 5. So how do you calculate the corresponding change in H? You do what minus what? Agree with that? 10.3 minus 8.5. Final minus initial. And so what do you get? 8.5 minus 10.3 is? Negative 1.8. Sorry, flailing. Okay. Where's Travis Daniel? Tell me another change of 1.5 that you did.
7 to 8.5.
7 to 8.5?
Yes.
And tell me what you computed to compute the change in H. What did you do to find the change in H?
I subtracted the 6.1 down to 4.3.
Okay.
And since I go decreasing, it's a negative number.
But you don't have to know that it's decreasing, because if you just do the subtraction, it will be negative. So
4.3 minus 6.
right, 4.3 minus 6.1 gave you
Negative 1.
negative 1.8. All right, where's Ori? Tell me your next. Tell me your change of 3. Your first change of 3 that you did. 7 to 10. And tell me what you calculated to get that corresponding change in H. 2.5 minus 6.1, and you got negative 3.6. Okay? And so there are so you guys got choices, and then your changes in H should look like this. When you fill out the table, did you get these changes in H? Okay, so we've got these changes in T and these changes in H, and we want to ask the first question: what is our first mathematical implication of constant rate of change? What's the first mathematical implication of constant rate of change? So we want to look at the change in H over the change in T. And we want to compute that for all of these. And what did you find? For all of them? You should have found that no matter what delta H you took divided by its corresponding delta t, you always got negative 1.2. Okay? What is this? So what does this indicate? We have constant rate of change. We have constant rate of change because we have the changes in the quantities, or the ratio of the changes are proportional. The delta H over delta T is this constant, negative 1.2. Okay, what about ratios of H to T? So what if we did ratios of H to T? So I've got a few in here. I'll do those in something else. Let's do, doesn't matter, orange. Okay? Here's some ratios of H to T. 10.3 over 3.5 is 2.943. 6.1 over 7 is 0.871. And 4.3 over 8.5 is 0.506. Do we have a constant ratio of H to T? Okay, so do we have constant rate of change between H and T? No, we don't. Is that right? What's the criteria for constant rate of change between H and T? That what is in a constant ratio? What needs to have a constant ratio? The change in H and the change in T. So here the ratio of H to T is not constant. Do we have constant rate of change between H and T? How soon they forget? Does the change in H and the change in T maintain a constant ratio? That's the criteria for constant rate of change of H and T, not if H and T maintain a constant ratio. Do we have constant rate of change of H and T? Yes. We just did it over here, 1.2. The ratio of the change of H to the change of T is negative 1.2. What are the units on that? What per what? Meters per second. What does it mean in this situation? It's the speed of the flag, right? And it's going down because positive height is up. And so we got a negative. So the height is descending, the flag is descending at 1.2 meters per second. Okay? Whether or not you have a constant ratio of H and T does not tell you whether you have constant rate of change between H and T. It's the ratio of the changes. The ratio of the changes. Okay, and then the other two criteria, do you have a constant multiple? Delta T times a number always gives you delta H. Yes or no? Yes. Negative 1.2. And then the last criteria. Whenever you have the same delta T, do you get a consistent delta H? Yes. There it is. Anytime you had a delta T of 1.5, you got a delta H of negative 1.8. Anytime you had a delta T of 3, you got a delta H of negative 3.6. That's the third.